everyone. Good afternoon. I hope you got some lunch before we have a pretty cool, discussion today about building a service for data collection of observability data with OpenTelemetry. A little bit about myself. Again, I am a OpenTelemetry Governance Committee member. I have contributed to OpenTelemetry for many years now, and also I'm deeply involved in the observability space. I also am a co-chair of the technical group for the CNCF on observability, and also represent Apple on the CNCF governing board as a member. Again, very happy to be here. Scale is one of my favorite community conferences, so thank you for joining in. And again, we can maybe keep the questions for the end of the session. But if you have a burning question on a particular slide, again, we could go through that too. With that said, again, I wanted to kind of touch upon very briefly for what observability is. How many of you are actually working in the observability space? Some of you? Cool. And as many of you may have already worked with the distributed systems, how many of you are familiar with monitoring systems? Most of you. So that's pretty cool, because from the days of Linux and really working through understanding what system behavior looks like, monitoring has been a very pervasive part of distributed systems. And today, observability is not only monitoring, but it is also the ability to collect, to analyze, as well as to alert and to visualize the data that you're collecting, right? So it's a bit more larger of a space than monitoring itself. That said, observability, again, leads to an active understanding of system behavior. It's not after the fact, typically real time. Tracking the dynamic systems, states of a system, so very much driven to understanding the system health at any given point in time and how the systems are behaving, and takes into account uncertainty and variation in behavior, which means that if you're seeing any abnormalities or any kind of variation in behavior, whether that's good or bad, again, observability tracks that real time. So many of you who are working with cloud computing systems, again, how many of you are using cloud-native systems today? Some of you, I'm sure, are. And as you know, in the world of cloud computing, whether that is Kubernetes-based or non-Kubernetes, there is a lot of high cardinality data that is collected for observing systems, all the way from the OS to the hardware, all the way to the application, right? So there is a fire hose of data that is coming in. So you need to kind of be very conscious of, hey, we've got an enormous amount of data that we're collecting for telemetry and observing systems. There is the, again, not only our computers and systems emitting telemetry, but also networks, devices. And typically, in a large network, you have literally millions of devices that connect in, especially if you take in the edge systems, right, along with the cloud computing core. System scale, compute power, commodity infrastructure, all of these combined together, running on the backbone of the internet, really makes the complexity of the telemetry data that we are collecting to be really, really high volume and high performance, right? So that leads to the fact that, hey, we really need to understand this data to analyze it and visualize it. So what's OpenTelemetry? How many of you have heard of OpenTelemetry? Cool, some of you have. So OpenTelemetry is actually a very large open source project. It's really unique in many ways because it represents a modern open source project, which, again, as being part of the CNCF, is the second most active project on the CNCF landscape after Kubernetes. So it is that active. It has literally thousands of developers who have contributed to the project over time. And OpenTelemetry, if some of you have worked in distributed tracing or in metrics collection, many of you may know it was actually the merger of two older projects, OpenTracing and OpenCensus, that led to the creation of OpenTelemetry. And much of it was because the two projects, at that point in time, this is about 4 or 5 years ago now, were literally, working on similar implementations, similar concepts. So the two communities decided to combine forces together, and that was the inception of OpenTelemetry. That said, it's a very popular project, very welcoming, very open, and it really builds a new telemetry system for processing all kinds of telemetry data, whether that is traces, metrics, logs, and even profiling and other parts coming in. OpenTelemetry is providing standardized vendor-agnostic components, and very unique to also the project is an observability specification, because many projects, typically will take a standard or an specification from a different organization. Whereas in the observability space, one of the things that has happened is that the specification of what is being built for OpenTelemetry is also on the project itself. So it serves as a very good way of actually having a standardized requirement spec, which then is also implemented in an open source way on the project, right? And so you have the implementation as well as the requirements, both on the project itself. The other unique aspect of OTel is, and OTel is just the abbreviation for the project, is the protocol and the definition of a data transport protocol. And that's called OTLP, which means it basically provides the schema for how you actually share or collect data and what that schema is for sharing. That's traces, logs, metrics, or other kinds of data. So there's an actual protocol that's defined. Along with that, there are client application instrumentation libraries, which means that when you're working with applications, how do you actually go and compile that and build it with your OpenTelemetry SDKs and APIs so that you can collect telemetry data from them. And those integrations are available in 11 languages. Java, JavaScript, and 9 other languages, very popular implementations. Java has auto-instrumentation. Python also has auto-instrumentation. So some of these languages come out of the box with auto-instrumentation. And then last but not least, and very large component, is the collection agent called the collector, which is used for receiving, transforming, and sending telemetry data to a backend data store, right? So several components. And currently, also another very interesting area that is actually being worked on the project is the implementation of semantic conventions. And again, this enables other integrations to be easily using these semantic conventions to interoperate with OpenTelemetry to send data, right? So it opens up the number of data sources that you have to be able to send data through OpenTelemetry. And last but not least, the project has a deep commitment to ensuring interoperability with existing protocols, Jaeger and Zipkin for traces, Prometheus for metrics, and Elasticsearch for logs. It's something that we are working on the project. If you're interested or use any of these big monitoring components, then you should be able to interoperate on the data level. So that said, again, you would ask, so why are we talking about OpenTelemetry? Why does it matter? Is it just another project that's super popular right now, or is it, what does it show? And I just wanted to call out that OpenTelemetry really represents the future of observability. It is driving the commoditization of the agent infrastructure, which means that back in the day, a decade in the past, or even 5 years ago, you had customized agents that each vendor was providing, right, with their bells and whistles and all kinds of unique features that you'd have to go and license an agent for. Whereas here you are, fast forward 2022, 2023, you're seeing that that commoditization of the collection agent infrastructure is all open source. And what that means is that you're getting all that feature richness in one set of APIs, one collector, one processor that most of the vendor industry has agreed upon. And all vendors are working together on this project to make available as a collector, right? And as a set of libraries that you can use to instrument your applications. And that really changes the landscape in terms of providing a vendor-neutral, industry standard-based, specification-based, agent architecture. What that does is that it pushes the value into the service side, right? That is the smarts and the data processing at scale of the telemetry data that is being collected is on the back end, right? And the high cardinality data that is being collected from many, many devices or many, many components on your infrastructure is then getting pushed to an service, which is typically, again, used for analyzing at scale as well as visualizing. But the collection with OpenTelemetry basically has become instrumented once, deployed everywhere. It's the standardized, framework. It also, in one sense, what OpenTelemetry represents is it's the foundational infrastructure for the automation of smart systems. That is, what is our goal? Can we actually have self-healing systems in the long run? Because it's very hard to maintain complex networks and complex architectures across not only cloud computing infrastructure, but also systems level server-side infrastructure and application infrastructure that might be devices, your phones, your tablets connecting into the space and talking to each other, right? So the idea is that, hey, does this lead, this kind of convergence of agent infrastructure lead to self-learning, self-healing, self-evolving systems? And it really provides the foundational thinking for leading even towards intelligent root cause analysis. And last but not least, because we are in the world of Kubernetes and containerized orchestration, several deployment modes come out of the box with OpenTelemetry that really makes it very flexible and very scalable. So with that said, I'm going to switch gears a bit, because here we are. We wanted to talk a bit about, what does OpenTelemetry provide us in terms of if you were to scale it up to be a service, right, for data collection, and you could send data to it. So I'm going to talk a bit about the requirements at a high level, because at the end of the day, typically when you have, large networks and large cloud infrastructure, systems for your organization, from a customer point of view, typically the requirements are that, hey, I want multiple users, hundreds of users, thousands of users to be able to use this observability data that we are collecting, or should be able to send that data to you. There's a high volume of data, that is, you should be able to pump and stream data through to this observability system. Should be highly available 24/7 if possible, and should be highly secure, easy to configure, easy to deploy, right? This is kind of a checklist that if you talk to an user, an end user, this is what they need. This is what they want. It's not a single user system. It's not low volume of data. Each one of these is very critical in building a system at scale. And on the service side, again, and I typically use the word service for microservices. Think of it as a microservice. We need to be able to support multi-tenancy for multiple users to be able to use such a system. Data streaming capabilities for being able to pump through high cardinality, high volume of data. In order to make it high volume, make available the service on multi-regions or AZs, availability zones. For security, again, to put in a robust architecture for authentication, for authorization, and for data encryption, both at rest and in transit. For easy configuration, again, having an easy to configure, configuration-driven option to be able to, again, deploy the collection to different clusters and at the pod level, and being able to send data to a push-based endpoint. That is all I want to do is just send data, right? And it'll go and hit the service at an endpoint, and then I should be able to do whatever I need to do after I've collected it. So most of these are requirements typically at a baseline in order to build a scalable solution which is used for collection. So I'll talk in terms of the control plane and data plane. How many of you are familiar with the terminology? Some. And control plane and data plane is typically terminology that is used in the cloud-native space when you're building microservices. Many of the large cloud providers also use the same terminology. So for a particular service, control plane and data plane is a way of looking at the control plane setting the policies and the data plane executing them, right? So you can have configurations and policies defined by the control plane, and then you have the execution components in the data plane. Control plane functionality also includes configurability. What kind of configurations do you want to run and deploy on your cloud infrastructure? Extensibility, that is, how do you extend this across different interoperable architectures, as well as features that drive this, the execution of this collection service, and a UI to be able to, again, configure, right? Or an API. So you could have a CLI and an API, or an API or a UI itself to set policies for normal behavior of the service. And again, this is very specific to, you're setting the paradigm up for being able to run the service, right? And that's typically what the control plane will support. On the data plane side, which is, again, there's a lot of complexity here. There are 4 typical areas that you are looking at when you're really scaling up to build a service, right? So this is like if you were building up a service, for literally thousands of devices and thousands of components, being able to, and workloads, data workloads that are being set up by users, and then being sent to your collection service. So some of the design considerations fall into these 4 categories. You want to be able to guarantee reliability, scalability, security, and observability, right? So you want to make your service reliable, which means that you are building well-tested, feature-stable code and shipping that and deploying that as part of your service. You have automated CI/CD, testing, build, and release cycles. You have regular deployment cycles, so the regular cycles for being able to push changes for the service. Itemize your dependencies. This is very important because it is a requirement now, as many of you may know, even with the security dependencies that the SBOM process includes, but it also affects the way that you actually build your components and deploy them for your service, right? So you need to understand what version of the dependencies are mapped into which version of your components that you are shipping for your collection service that makes, again, a full dependency tree. Along with that, you also want to guarantee high availability, which is very integral to providing reliability for a service. And what that means is that you have to have failover design, backup. Failover could be, again, failing over to a different AZ or a different instance or just, to a different region. Backup, disaster recovery, and also being able to manage your routing for, the network layer, right? Which means that these are considerations where do you have, multiple AZs that you are switching over, and you are guaranteeing no single point of failure, right? Which is what SPOF indicates. And last but not least, global configuration, so that if you're operating a service globally, where you have a collection, endpoint available in, say, US East, Dublin, and Singapore, you have, the same switchover and the configurations available across these regions, right? So reliability is an important area to consider in your design for your data plane, so that the service is extendable and reliable. The second part is scalability. And again, this means, first of all, performance. When you define your SLOs for the service, performance is a very integral part of that. And that means that you have not only resource allocation that you have already kind of designed your system for, and your service for, but also performance in terms of data throughput, right? What are you able to guarantee that the service can ingest? And if you have any kind of buffer capacity, can you auto-scale and scale up dynamically, right? And that comes with capacity planning that is related to the infrastructure that will give you that auto-scaling capability. At the lower layers, you have dynamic traffic management, as well as hardware configurations. What type of instances are you deploying? What type of network failover are you planning? And the data storage that is associated with each one of the regions or each of the clusters, right? So again, each one of these areas is being designed and accommodated in your scalability requirements. And another interesting area, which we kind of often take for granted, but is actually a pretty important part in leveraging and extending scalability for a service, is what programming language you're using, right? So often, when you're building a cloud-native service, it could be Java. Many times it's Java, because there are many capabilities of the language itself that you can leverage for scaling and performance. And Go is also very typically used nowadays on observability infrastructure, right? So if you're building a service, especially OpenTelemetry, most of the core collector is, all the core collector is written in Go. And there are also libraries in 11 languages that actually interoperate with the collector to be able to send data, right? And for many of you who are familiar, maybe it's Prometheus. Prometheus is in Go. And any extendable multi-tenant implementations of Prometheus, such as Cortex or Thanos, are also in Go. So Go is becoming very pervasive on that infrastructure layer, and typically a lot of benefits for performance are typically derived from the language itself. Then moving on to security. Again, this is kind of the heaviest part of the discussion here today. You need to factor in what your authentication policy is. How do you, again, for many of the cloud providers, they have their own authentication schemas. AWS, for example, has SigV4 as a handshake that is used for authentication. So again, planning that out in terms of how your endpoint connects in with your application data and what is needed there is important as part of your security architecture. Authorization and access control, that is who has access to view-only data versus read-write. Transport level security, TLS, with encryption in transit and encryption at rest for your data that is being sent for telemetry. Often, especially if you're looking at security use cases, for the data that you're sending for telemetry, also may be encrypted. So again, that also affects performance, and that's another area to be aware of. Secrets management. What are the credentials that you're sharing, and are they encrypted or are they stored in a place where it's not visible, when you're sending it over the wire? Data security and SBOM, right? Again, these are areas that you do need to address in your security architecture as you build the data plane out. And last but not least, again, making your collection service observable, because the components itself of the service that you're running to collect should be instrumented for monitoring system health. Are they healthy? Are they operating as normal? Are they frequent, performant? Are they in, in line with your SLO definitions, or are they, abnormal? And defining the alerting thresholds at which, if some abnormality is caused, then to be able to take that and alert on it and be able to act on it, right? That is, if your service is not behaving healthily, what do you need to do in order to bring it back into normal behavior? And last but not least, again, and I'll talk a little bit about runbooks. Again, how many of you are familiar with the runbooks? Anyone working on cloud-native infrastructure? Again, we run with runbooks. Again, that's something very typical in large organizations. It's very important. It's really an operational guide for both the support teams as well as the engineering teams who are building and running the service to be able to go off the same sheet of music, understand what the service does and what normal behavior is, so that if there is a failure, you can triage it, right? All right, so moving on from here, again, I want to talk a little bit about architecture, because I'll propose, some, step through some of the ways that, the data flows for an observability collection architecture. So many of you, again, I talked about OpenTelemetry, and this is, again, an OpenTelemetry-based collection service that we are talking about. So many of you may have seen this diagram already on the OpenTelemetry.io website, which is the project website. And what this does is it shows you, on the left-hand side, the microservices that you can collect code from and instrument with. So in yellow, these components that are listed out are the components that the OpenTelemetry project builds, right? And all of us who are contributors to the project work on. So you have your application code, for example. So it could be an application, which is a web-based application or is a client app running on your mobile phone that is instrumented for sending telemetry. It could be as simple as, again, P0 failures that are occurring on the application that are then instrumented with the OTel API and SDK. And then sent to the OpenTelemetry collector that you see in the center, and then sent to a database on the back end, right? So it could be time series for metrics. It could be trace databases for tracing. It could be column stores for logs. And then visualized through front ends for visualization. Then you also have the lower layers on the left-hand side, which is the infrastructure. Right, and you are typically, many of our cloud-native infrastructures are running on Kubernetes, as well as on cloud providers, right, which is shared infrastructure because, again, there's a whole layer of complexity all the way from the network to OS to the hardware that is being available in a multi-tenant form back to what we are using on the application layer through Kubernetes. And all that telemetry that is coming from each one of these layers is being collected through an OTLP protocol, sent through the collector, and then sent to the backend, right? And that's typically what collection means. It's instrumentation of your application and infrastructure, formatting it into OTLP, sending it through the collector, sending it to the backend, right? You can also instrument system services like databases and APIs, and then send it. All right, so moving on. Again, I kind of wanted to talk about this because this is, again, a proposed way, one of the ways that you can actually configure a control plane and data plane for a collection service. And often you will have an assortment of data sources. That could be your applications, your infrastructure, as we were just referring to in the previous page, the previous slide. And then being able to actually make a service endpoint that goes and hits, sending data and can push data to the service endpoint, which then talks to a service broker, which sends it to a set of collectors that are actually scaled up and spun up in multiple instances based on the cluster configurations that you have and the infrastructure configurations that your application runs on. So you can potentially spin up, multiple collectors, and typically in the OpenTelemetry world, a collector typically runs on a cluster, right? And a cluster is typically having multiple nodes, so multiple pods that you can run and collect metrics from, or if you have instrumented for traces, you can take traces and run that. Scrape managers are used for metrics, again, in order to scale up the ability to shard and collect metrics from multiple sources, right? And there is an feature called the target allocator that is built into the OpenTelemetry collector that you can actually implement with an operator. And these are, again, internals of how you would implement this, where you can typically use a scrape manager, go and collect, and then be able to send it, process it for exporting. If you're sending it to a particular backend, you should be able to then just push it and export it through the collector. Right? And there are a whole set of configurations that are managed. Again, I will leave that up for Vijay, who is going to be speaking next in the next session, because he actually will be diving into some of the application configurations that he had implemented in the installations that they did for a dynamic example of a collection service, right? So this is in general, though at a high level, when you're building this out, you really are, spinning this up on a cluster by cluster level and being able to really scale up the volume to the volume of metrics and traces coming in, right? And then being able to export that out. All right, so just for those of you who are super interested in the collector's innards, each one of these collectors, as you saw, the boxes there, purple ones, you can deep dive into them, and this is how it looks like internally. The collector is actually a very composite architecture because it has several components. Typically, it has 4 types of components: a receiver for receiving data, different types of data that could be metrics, it could be logs, it could be traces. Then you have extensions, which are, again, additional components that actually help you extend or understand the health, for example, or for the collector itself. Then you have processors, which are typically used for aggregation or pre-aggregation or massaging of the telemetry data that you're collecting before you send it, export it, right? Send it to a backend for a data store. And then you have also other types of processors, like for doing Kubernetes, metrics that you're collecting. You could aggregate it, you could process it and in a processor and then just send it. You could attach labels, using your attribute processor. So there are different types of processors in the collector that you can leverage for being able to really massage your data to be ready for export so that it's consumable right out of the box. And then once your data is ready, for sending to a particular backend, you may have a metrics backend for Prometheus, or you might have, a trace backend like Jaeger, or you could have OTLP, sending it to a log database. You can use an exporter and just send it, right? And there are native OTLP exporters that are available in OpenTelemetry core. And then you also have different types of exporters like the Prometheus remote write exporter or the Jaeger and Zipkin exporters, as well as other, numerous exporters for third-party integrations. Like, for example, some of you may be using a particular vendor, right, on the back end to be able to visualize. So you have exporters typically that can just transform the data and just send it to that monitoring backend. As I have called out on the bottom, profiling is something that's a new area that the project is starting to dig into. Again, eBPF, for some of you who are familiar with that, is an area which is super interesting. It's also other metrics that you're pulling in from the Linux kernel, as well as other, lower level real-time metrics and logs, which I think is probably more foundational than anything else. All right. So just let me do a time check, and I think we're doing well. Last but not least, I wanted to kind of, again, share this from a service standpoint, right? Like, what does this mean? Once you have architected your service, once you've taken the requirements, designed for it, both on the control plane and the data plane, you have an implementation. So how do you operate this service, right? Because long term, you need to run this service at scale to be flexible, maintainable, and secure. And that's something that, again, is typically done at scale with runbooks. So just wanted to call out what a runbook entails at a minimum. SLO definitions, like if you have P99, 99% availability or higher. Typically, those are the category of services that you actually say is a service. Otherwise, you're just running a system. You use your system design and implementation documentation as a background for, again, both the support teams as well as service teams being able to use that. And typically, in best practices in a runbook, this is very useful because you have an understanding of the architecture and the components that are implemented to support a collection service. OpenTelemetry, as you can see, the innards are there. The collector is the main part, and then you have APIs and SDKs. So those are components that are pulled in from upstream. You might be adding some more components in that collection service before you send it, right? And then understanding what the errors and failures are, right? Which are known errors and failures for different types of telemetry data. And that means that you not only want to be able to itemize what abnormal system behavior looks like, but also understanding what these errors and failures are, how do you identify them, how do you detect them, triage them, and then what are the recommended solutions for bringing back into normal behavior. Because that typically then helps the engineers who are working on these services to be able to root cause a problem that may be occurring on the service. Similarly, defining a clear process for triaging and identifying root cause is very important because when there are service failures, especially when you're running on cloud native infrastructure, it could be at any layer, right? It may not be even the collection service that you're running. So you really need to understand, what are some of the symptoms and being able to triage that to then assign the root cause to the service that is operating abnormally. It may be something that, DNS was out, and hence you lost data on the collection service because, you retried, failed, and you lost data, right? But it wasn't your service, really. It could have been an outage at a lower layer, and you need to be able to triage that and root cause it. Similarly, also having a process for escalation where, if you have cross-service dependencies or lower-level outages, you have a clear path for escalation, and being able to communicate with other teams is super important. Because when you're running and operating a service where you're guaranteeing 99% or higher uptime, you need to be able to have that, implementation and policies very clearly defined. Service restoration practices, again, if there is an outage, how to communicate that both to your customers, your end users, as well as internal stakeholders, and being able to do a retrospective where you have a detailed analysis of what the failures were is very useful. And last but not least, this runbook, should be a living document because, infrastructure changes over time. You may have started off with specific type of instances for your clusters and your nodes, and you might have upgraded to a Graviton, for example, right? So again, when you change hardware, that brings in a whole layer of complexity, and so your runbook should be kept up to date in order to maintain and operate a service at scale. All right, so that said, I think I'm done. I would like to open it up for questions. Thanks. No, it's all good.
So, any questions
No questions?
Don't be shy.
All right, this is good. This talk will be recorded, so you can always go back to it. And if you have any questions, I'm available typically on the CNCF Slack. So if you are on the CNCF Slack spaces, please reach out. And if you are using OpenTelemetry, again, in particular deployments or configurations, happy to help.
Last chance.
Last chance. Hope you enjoyed the talk.
You're good at the talk.
Thank you, everyone. Thanks, everyone.